Hello everyone, it's Calder from 19. Today's day 84 in my challenge day. What I'm going to do is assessing meshy data from the triangle intersection between the ray and the triangles. So in the previous video, we could just get the right-centric coordinate from the triangles, which is used for the local transformation of the triangle, like interpolation inside the triangle. But when we want to compute some kind of reflections or the diffuse effection on the surface, we need the exact coordinates of the triangle in the world space perspective. So in this case, we need to accessing the mesh data in terms of the global coordinates, not the local one. So, okay, let's start. First things to do is to create new storage two buffers for the vertex buffer, and the other one is for indices buffer. So let's find the bind here. Okay, I just created a new two bindings here. The type is storage buffer and the stage is for compute shader. And then the binding number is 2 and 3, which is the next number of the acceleration structure binding. So to write this binding, to write these descriptors into the set, we need to prepare for the two additional write description set struct for these two buffers. So in this case, this buffer is find similar PK descriptor buffer info like storage buffer as our render output. Let's change this name as vertex buffer descriptor index buffer descriptor info. This buffer name will be vertex buffer. The buffer size is it used the range as a PK horse size. So let's increment the size of the array as a 4. This index will be follow 3, 2, and 3 as its binding number. And we need vertex buffer description info, index buffer description info. And make write required the binding number, so 2 and 3. Is there other things to do? You insert to the scripture size. Okay, I think this is enough. So let's try to run it. It was successful. Okay, so we run the render doc. Without HDR. Yeah, it's still same, so there's no problem. Let's proceed tutorials more. So if we create new descriptors inside the application side, purpose is that we want to read and write it in the shader. So what we need to do the next is trivially make a binding, a layout qualifier, and a storage qualifier to specify the descriptor, these two new descriptor for vertex buffer and index buffer in the shader. So let's add new binding here below the TLAS to set is equal to 0. This is a buffer because it's a storage buffer. And we will call it as vertices. The layout binding 3 set is equal to 0. The buffer is indices. UVac indices. Nope. It's UInt. indices. Let's build it. No problem. To make sure that we can access this buffer correctly, let's visualize the first vertex of each triangle. Replace the first branch of each segment in ray trace column. Int primitive ID, primitive ID. Recurring at intersection instance custom index extension. No. By calling the recurring get intersection primitive index extension, we can get the primitive ID of intersected triangle by ray. So we get the triangle index. This triangle use index is 3. Reply. So our triangle has a identifier as this primitive ID, and this primitive ID, this triangle is composed of 3 indices, which is point to the vertex. So in this case, it's basically we can get an index included in the triangle. So in this index 0 is will be same with primitive ID multiply 3. This is the first index of the triangle. This is just formula of the triangle we will use. And if we want to get our vertex, factory and the V0, we get vertices with the index 0. So finally, we got the actual vertex coordinates from primitive ID, which is the triangle intersected with the current ray. So we can remove this part and just try to test about the pixel color. Pixel color. Factory 0.0 plus three zero. By the way, we can just modify this value as like this. Yeah, as you can see, now we can show that the triangle composed this part, but it's slightly different. Should now be able to build and run the application. Get the following if the bird is. Okay, let me roll back. What's the difference, I think? First, I forgot to add a dollar keyword here. Still doesn't change it. You int x-ray. Three. So let's just proceed the tutorial right now and debug it later. So because we could check the vertex and the indices extraction works well. So we can get the remaining indices and vertices the same way. So called primitive ID. Two, 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 like this. And then we may can get barycentric coordinates of barycentrics. Ray, Curry, intersection. So by using these barycentric coordinates, which is the weight of the intersection points, these coefficients give us the information about the intersection point in the local coordinate as a local coordinate in the triangle. But we have actually the global position in the vertex of the triangle as the vertices. So if we multiply with the barycentric coefficient and these vertex, we can get the global position of the intersection point in the word space. Hmm. Object space intersection centric. By the way, is it the right pronunciation from the right century?
Barycentric.
Barycentric. Okay. Not barycentric, barycentric. So by multiplying each coefficient to the vertex, we can get the object space intersection points in terms of the word space coordinates. So that we can use these object space intersection points to coloring the pixels. Yeah. So finally, I think we can. It seems that we could draw some information about the how can I say that as a true intersection point in terms of the global word space, and I could visualize it just with a simple coloring method. So the tutorial also said that. So I just repeat it. So meshes specify the locations of their vertices in their own coordinate space, which is the local coordinate space, and called the object space. However, the camera traces ray in word space. So we placed meshes in word space by specifying its translation, rotation, scale, and skew using the object to word matrix. This is a transformation matrix. Uh, so in the traditional graphics pipeline, there's some of the metric transformation steps to transform the model from the model space to the perspective projection space, screen space, actually. So that it means we start from the model space. For example, the model can be modeled in the Blender coordinate system, and then you export it to our application. At the moment, we only have the information about the model space, which is the local transformation. And then by using the proper matrix transformation, we can apply the word transformation, like as I said, translation and rotation, scale and skew. And these transformation matrix information is uh, stored in the our acceleration structure, which is top level acceleration structure with the field of transformation matrix we set in the main CPP. But we didn't transform anything about our model. So we just used the identity transformation matrix, which just uh, causes the same transformation. That means we didn't apply any transformation on the model. So it's just same. So word space and the object space are the same because we didn't apply any transformation on it. Now building random position. Okay. Time submit. Still same. JT service. dices. Is there mesh the size? Change shape, mesh, meshes, pushback, vertex. Simulation structure built into read on the beat. Is a large numerical rounding error can cause initial potential. Getting a triangle normal is really easy. So let's suppose that triangle triangle is composed of three vertices, which the name is 3, 0, 3, 1, and 3, 2. Get on two arbitrary edges of triangle of the triangle by using vector calculation. Edge one is can be a v0, v1 minus v0. E2 is v2 minus v0. Let me just like this. And we can take the cross product. So if we take a cross product operation of two vector on the same plane, we can get a vertical vector. No, we can get a vector which is orthogonal to the two vectors, and which is called as normal vector of geometry. A surface, I think. Yeah, surface would be better word. Take normalize. This is not normal vector yet. Normalize the orthogonal vector, then we can get a normal vector of the surface. Triangle in this case. So with this just simple formula, we can get the normal vector of the triangle, each triangle, and this is composed of the counterclockwise, the vertex, each vertices are ordered in the counterclockwise, but it depends on the graphics API, but we use this in the Vulkan API, and we can use this normal vector a lot of case for to compute the reflections on the surface to calculate the outgoing direction in terms of the specular, the perfect specular, uh, ideal specular reflection just reflected on the surface with the same angle, the incoming angle, which is the radiance, and the irradiance are just has the same angle. So in this case, the normal vector is really useful to compute these kind of reflections. And I will do that in the next video. Okay, anyways, this is end of today's recording. And as always, thanks for watching and see you next video. Bye bye.